Have you ever wondered how drones can fly? In the last video, I showed you how to control the speed of a motor. But something needs to give the speed controller the right speed commands. So enter the flight controller. This little guy is making 8,000 corrections per second to the motor speed to stay up in the air. Or for FPV drones specifically, to follow the stick commands that you give it by the controller. In this video, I'll tell you how it works and how I designed my very own flight controller. Let's take a step back. How does the flight controller even know what orientation that the drone is in? Enter the IMU, or Internal Measurement Unit. This thing houses a 3-axis gyroscope and a 3-axis accelerometer. Using the accelerometer, we can get the relative orientation of the drone with respect to gravity, which is a constant 1g acceleration pointing down. The gyroscope measures the rotational speed of the drone. It's worth talking more about how an IMU actually measures things though, because it's really cool. It's based on MEMS technology. Inside of this little package there are weights that move when you move the drone. To measure how much the weights move, we have these fork structures which form a capacitor. If one side of a capacitor moves, the capacitance changes and we can measure that. But how does a flight controller use this? In simple terms, the flow of information looks kind of like this. You, through your transmitter, send a signal to a receiver on the drone. That signal then becomes the set point, which is the rotational speed that we want to have for each axis individually. Then we read the actual rotational speed from the gyroscope, and the difference between the two is the error. And the algorithm that we use to minimize the error is called a PID controller, which is used in everything from your thermostat to your car's cruise control. It is very good at reducing an error as quickly as possible. And you'll find a million videos of this online, but I'll try to give an intuitive sense for how it works. There are 3 terms. The proportional term is the simplest. This term increases proportionally as we get a bigger error. The integral term is to remove what we call steady-state error. This can happen, for example, if one motor is weaker than the other or one side of the drone is heavier. This term keeps rising more and more the longer that the error exists. This could also mean that the I term goes to infinite if the error never goes away, so we usually want to limit it in some way. You can see it here when I try to push this drone down. You can hear the motor spin up more and more and more to try to push back up. The derivative term reacts to how fast the error is changing. It takes the time derivative of the error signal. The faster that the error grows, the bigger the D term becomes, and the harder it tries to work against the rate of change, effectively dampening the movement. So when the wind hits the drone, or I push it down quickly, the D term shoots up and the motors react to slow that rate of change before P and I even get a chance to react. That also explains why the D term is so sensitive to noise, because noise is literally just the signal going up and down very quickly, so its rate of change is huge. Noise can be introduced by many things, including electrical noise and mechanical noise. Electrical noise on a drone is everywhere. The flight controller sits right on top of the ESC, which is constantly switching MOSFETs at high power, generating all sorts of magnetic and electrical fields that can cause interference by inducing currents and thus voltages inside of the IMU or on the traces running to the IMU. The flight controller also has 2 buck regulators, one for 5 volts and one for 10 volts. A buck regulator is literally just an inductor switching rapidly, which is, again, a massive source of interference. To mitigate this, we're going to give the IMU its own regulated power supply and place it as far away from any of the buck regulators on the board. Mechanical noise is also everywhere on a drone. The motors cause vibrations that are not only quite large, but also constantly changing in frequency as the motors spin up and down. The motors vibrating also cause all of the other parts of a drone to vibrate a little bit at their own resonance frequency, but most importantly, the frame. Everything in the world has a resonance frequency, and by designing a frame that spreads out this frequency over a large spectrum, this gets better. But we can also try filtering it out. Betaflight actually has a lot of ways to help reduce and filter noise. It's easiest to just follow the gyro data signal path. When the data enters the flight controller, we first apply an RPM filter. More on this in a second. Then we have static notch and dynamic notch filters on the frame resonance frequencies, and also a low pass filter to clean up a little bit. The RPM filter though is by far the coolest one, because the flight controller commands the speed controller to spin the motors, but on the same wire, the ESC sends back information of the speed of the motor. If we know the speed of the motor, we can apply a dynamic notch filter right on that frequency. For a drone with 4 motors, that is 3 harmonics times 4 motors on 3 axes, which is 36 notch filters, just for the RPM filter alone. All of this filtering is done to get clean gyro data. The PID controller then gives you 4 numbers: roll torque, pitch torque, yaw torque, and total thrust. To get positive pitch torque, you spin up the back motors and spin down the front. To get roll torque, you do the same with left and right. Yaw torque though is a lot less intuitive. Motors that are diagonally from each other spin the same way, and by spinning up these 2 motors and spinning down these 2, in order for the drone to preserve its total angular momentum, the drone itself must start turning into this direction. Okay, well, that was a lot of math and stuff. Let's talk about how I actually made the flight controller itself, and also what makes this thing quite unique. Pretty much every single FPV drone flight controller runs on STM, F4, F7 or H7. But Betaflight supports much more than this, and recently Betaflight was ported to the Raspberry Pi Pico platform. These chips are much cheaper at about $1, while not really giving up anything. So then I went ahead and I designed everything in KiCad using the RP2354B, which has internal flash. We've also got an SD card for logging black box, and OSD circuitry using the pin.io. Then I also did all of the routing, which was very hard because it's a very tight board. All of the files will be available in the description for free. And now for the moment that you've all been waiting for. Does it actually fly? But you haven't tested this?
Just another test in my basement.
Ah, in your basement?
Yeah.
Whoa!
Yeah, that seems like
So it was flying okay, but it had these crazy oscillations when you would do a lot of like a fast movement. So we tried doing some tuning and...
Huh, well then, there you go.
It flies so good, eh?
Oh, yeah. I mean...
What is it? What did...
Yep.
Bastiaan, we need to learn how to pitch tune. Like this is perfect. I want to fly the FPV. See if it's...
Yeah,
give it a shot.
This is perfect.
Now give it a shot. The battery's out. Don't.
To home function.
It flies so good. What the hell?
Turn away from me.
Literally 180 degrees away.
Oh my god.
Exactly away from me and drifted away. Up and away. And it was like at some point like.
But like when I punch it out, do you remember when I punch it out? It like.
Yeah?
I was in a cloud more or less, so I couldn't see.
What's up?
Listen to it. Nothing. Yeah, so I forgot to record any actual flights with the camera again. Whoops. But after applying like this random tune, like a preset, it flies pretty good. So there's still some things to iron out. If you want to help, let me know. But hey, it flies pretty good now.